Hello, everybody. Come on in. Ask questions if you have them. Sorry about the kerfuffle this morning. I'm feeling a little better now. My eyes were all swollen. I couldn't talk. My throat still hurt, but at least I can see and talk. So, does anyone have any questions before we get started? Looks like we got 7 of you guys in here.
I have a question. So is this going to be like a whole 80-minute class length, or is it like still to 120?
No, I wanted to cover new material, but I think it's probably fair for me just to get you guys to field any questions or answer me any questions you might have regarding the upcoming test and past materials more so. If there's not really many of those questions, I might actually just go ahead and at least solve some problems from chapter 10 and maybe even 11. But it doesn't have to be. Y'all are free to leave at any time you want. If you I get all of you to go ahead and chat me your first and last name. That'll be roll for today. Uh, but other than that, like I said, it's just a matter of this is my chance to let you guys ask me questions in preparation for the upcoming face-to-face test, which for the people that have me on lab on Mondays would be a week from today. But the other 241 students, they have lab on Thursday, so there's and there might be some 242 people in here as well, and they final on Tuesday. So, anybody have any questions?
I have a question regarding like Unit 10.
Okay, hold on a second. Kayla,
Oh, sorry.
I was just making an announcement to Kayla. She just signed in. Kayla, I just asked everyone to go ahead and chat me your first and last name so I can keep it as a roll. Go ahead with your question.
Yeah, so for chapter 10, you said it's all the rotational motion stuff is basically the kinematic equations, but with the angle. So, should we still be like reading all that material, or like what's the most important part of the textbook for us to understand there?
Well, luckily, none of that will be on this face-to-face test coming up, but it will be further material. So, in fact, the whole chapter is fair game. So I plan on covering it in its entirety. There is more than just the kinematics. The kinematics I wanted to cover just online or face-to-face just for a second, so you guys could get started on homeworks. But there's a dynamics portion of it too, where we learn basically Newton's second law for rotation is that the summation of the torques is equal to, you can either call it dl dt, which is the instantaneous rate of change of the angular momentum L, or you can say it's the summation of the torques acting on the system is equal to I times d omega over dt, or I times alpha is another way of writing it, where alpha is the angular acceleration. I is the moment of inertia. That's another integral type formula we can use. It's called, instead of having to do an integral in the numerator and an integral in the denominator like you do with center of mass, the moment of inertia that we use in physics is the integral of r squared dm, which you're going to discover if you're in engineering and you take statics and dynamics and strength of materials. You're going to find it extremely well, a somewhat different version of what we call our moment of inertia. And that's basically mostly because you have to change based on certain materials and stuff like that. So if I just say a DM, uh, that takes into account the density of the material. And with, for instance, in structures, when you're building structures and stuff like that, you have to know the moment of inertia to calculate the bending moment, as well as the sag that it gets, and all that requires knowing whether you're using spruce, pine, fir, or yellow pine or ash or stuff like that, or steel for that matter too. So that's probably way more than you wanted to know, but yeah, we're definitely doing some other stuff in chapter 10.
Okay, cool. Thanks.
You're welcome. Sorry for such a long answer. I wish I could answer simply, but I'm over
That's okay.
explaining. uh, Anybody else have any other questions? Okay, so chapter 10, just going over the contents of it. The first entry is section 10.1, which is angular quantities, and that's where I told you there's some parallel between the kinematic equations that we use specifically with rotational motion versus the kinematics that we used in linear motion. So in linear motion, we had A was dv dt, meaning the acceleration vector is the instantaneous rate of change of the velocity vector as a function of time. Additionally, the velocity v vector was d by dt of you could call it r vector, where r of t is the position vector of any object or system at time t equals 0. Well, actually not at time, at any time t, starting at t equals 0, of course, but yeah. So that's basically the first two variables, or three variables, that we learn in linear motion is position, which can be given by the r vector, or sometimes they'll call it the x vector as a function of time. Then if you take the derivative of that, you get the velocity vector as a function of time. And then if you take the derivative of that, you get the acceleration vector as a function of time. Well, it seems that those terms, like a linear distance, might not actually be quote unquote linear if you consider the distance that an object was going around a circle. And then in that case, that distance is an arc length. And we know that arc length S is given by the radius of the circle times theta measured in radians. So if you stick to radians, you have the nice equation that you learned from trig, which is S is equal to R times theta. You can take the derivative of that and you'll get Vs over dt, which is basically the velocity parallel to the circular motion. And that velocity, ds dt, is equal to r times d theta dt, which theta is the angular displacement, which normally would be measured in radians, but it could also be measured in revolutions, degrees, stuff like that. But that d theta dt is what we call omega, which is a pseudo vector to some extent, but it's a vector that represents rotational motion in such a way that basically if you curl the fingers of your right hand in the direction that something circular is rotating, so if they're rotating, for instance, this way around here, then your thumb points, using your right hand, of course, then your thumb points in the direction of this omega thing. So that's the angular speed, and it's normally measured in like in radians per second, but it could be in revolutions per minute or rotations per minute, all sorts of stuff. And then if you take the derivative of that equation, which was v is equal to r times omega, you get the derivative of v with respect to t is the acceleration. That's called the tangential acceleration. That's like what your speedometer would read, even though you're on a circular track and you're speeding up or slowing down. The change of that velocity from one point to another as a vector quantity is alpha, and that's, or excuse me, is a, and that's the tangential acceleration. But it's related to alpha by a equals r times d theta dt, or excuse me, d omega dt, and the d omega dt is the alpha vector, which has a similar definition for its specific direction. It's weird because it's got to be perpendicular to the plane in which the object rotates, but other than that, it's it. Okay, so we have these new variables in circular coordinates, or in rotational motion. We have these new variables, theta, which plays the role of x, or r. We have omega, which plays the role of v, and we have alpha, which plays the role of a. And in addition to those normal kinematic equations we learned in linear motion, like x equals 1/2 at squared plus v0 t plus x0, that becomes theta equals 1/2 alpha t squared plus omega 0 t plus theta 0. And for instance, v squared equals v0 squared plus 2 times a times parentheses x minus x0. That becomes omega squared equals omega 0 squared plus 2 times alpha times parentheses theta minus theta 0 close parentheses. So all those kinematic equations come out by just making the translation that x becomes theta, that v becomes omega, and that a becomes alpha, and you can just trade that in all those equations. When you get to the dynamics portion, we say we no longer have mass necessarily, we have a moment of inertia, and that's given by, as I said, the integral of r squared dm. but that plays the role of mass. So like if you had F equals ma, then by analogy, you think something related to the total force is equal to something analogous to m times something analogous to a. Well, that's exactly what it is. The thing analogous to force is torque, and it's given the Greek symbol tau, which looks like a cursive backwards T, if you will. It's a Greek letter. And they say the summation of those torques, that tau, is equal to I times alpha, where alpha, like I said, is the parallel to A. So you can look at it that way, which is what we did initially when we were considering just forces and masses that were constant in time. That just allowed you to use summation of forces equals m times A. This also allows you to use the summation of the torques equals I times A. If you want to go a little bit more complex and deal with possible forces that change as a function of time, you have to switch summation of forces equals ma to summation of forces equals either dp dt, which is the most general form, where p is the momentum vector of the system, or you can do m times dv dt. That works as well to solve the differential equation, but that's only true if the mass is not a function of time. So that's the big picture of the difference between rotational motion and linear motion. So we're definitely going to work some things on that. That's section 10.1, where I actually stretched it to talk about essentially everything all the way up through section 10.5. So 10.1 was angular quantities. Again, that's the theta, the omega, the alpha. Ultimately, you're going to learn when we get to the dynamics section, which is 10.5, that also has m becoming I, moment of inertia, and stuff of that scenario, or like p, the momentum, becomes L, the angular momentum. So 10.2 is the vector nature of angular quantities, and he talks about pseudo vectors there, and they have basically this property that shows they're not real vectors because the mirror image is not the same as the actual object for angular quantities. So that's one of the hallmarks of actual vectors, is they have to be the same under a mirror projection. So your book will tell you about that, and it's kind of interesting, but definitely keep that in mind. Think about something to think of just in terms of knowing the differences. 10.3 was a constant angular acceleration, so that's where they actually are giving you the idea that the summation of the torques is equal to I times alpha. And then 10.4 is where they talk about torque, and 10.5 is rotational dynamics, torque, and rotational inertia. And then 10.6 is a section on solving rotational dynamics. 10.7 is actually calculations of moment of inertia. As I said, was the integral of r squared dm. Then they talk about, since we already did dynamics, remember we did that first with Newton's second law, then we covered conservation of energy. Well, guess what? There's some terms we need to add to our conservation of energy equation related to rotational motion, and that's, exactly by analogy, the kinetic energy was 1/2 mv squared. In rotational motion, what we discover is that it's k again is equal to, in this case, 1/2 I, which, remember, that's the analog to mass, times omega squared, and of course omega is the analog to velocity. So 1/2 I omega squared is the rotational portion of the kinetic energy. So an actual object like a book that you throw has a kinetic energy 1/2 mv squared that's given by the velocity of the center of mass of the book. But as you threw it, of course, it's probably going to rotate and stuff like that. If that's the case, then you also have another term, 1/2 I omega squared, where I is the moment of inertia of the book and omega is the rotational rate at which it spins once you've thrown it. And then ultimately they talk about rotational plus translational motion. So you can analyze things like, not only does an object potentially slide down an inclined plane, if it's got enough friction, it will actually rotate. And if it's got enough friction, it'll do what we call rolling without slipping, which means for every millimeter of axis of I say every millimeter of, sorry about that, every millimeter of arc length that touches the surface it's rolling on corresponds to a millimeter of distance traveled. That's rolling without slipping. Any questions on that? Okay, so that's a rather full-throated explanation of the entirety of chapter 10. So Does anyone have any questions to prep them or to get help from the practice tests you've been taking in an attempt to try to do well on the midterm that's coming up?
I have a question about the topics covered in the upcoming midterm.
Yes.
So it's going to be up until chapter 9, which is center of mass, right?
Yes, up through chapter 9.
Okay. And it would be like the last midterm where like there's going to be other stuff jumbled within the first and second midterm.
Yeah, and I try to make the practice tests like that as well because all our tests are somewhat comprehensive. Sometimes I literally take that as exactly the definition of what I'm going to put on it. For instance, when I look back at the previous face-to-face test, if there's a specific problems that students had problems with, it's not uncommon for me to take that very specific problem and maybe change it a little bit and put it on a new test. So if you don't know how to do that, for instance, integral, if they give you a of t is equal to 3t squared plus 2t or something like that, and they want you to tell me what the position is at t equal 3.4 seconds or something, that's a typical problem that I saw a lot of students had difficulties with. So that's definitely fair game on the midterm as well as the final.
Okay. Thank you.
Okay. You're welcome. Anyone else? All right. Well, you guys aren't really necessarily what I call far behind. We are in chapter 10. My intent would be to knock it out on Wednesday or even today. But the main thing is after that we go to 11 and then we jump to 14 and 15, and 14 and 15 can both be covered each in a day. So in other words, I only need 2 class days to cover 14 and 15. Uh, Sometimes or usually before I get to 14 and 15, because I jump straight from 11 to 14 and 15, sometimes I actually cover relativity in there. I think I'm saving special relativity till the end of the semester so that if I have time, I can cover special relativity, which is, I want to say chapter 30, I think it's 34 or 35, something like that. Anyone?
How many like times would you recommend taking the practice tests? Because I know they have different questions that kind of like rotate. It's like, what's a good
Yeah,
measure?
I would say the hallmark would be if you can consistently score an 80 or higher, say uh, 3 or 4 times, then you're probably in a good space. If you can't do that, if you actually need to look up a lot of stuff to even get that 80, then probably you need to keep on taking it. But yeah, if you can consistently get an 80 or higher for 3 or 4 tests in a practice tests in a row, then I say you're probably pretty good and ready to take it. If it's literally only those 3 or 4, maybe you might want to take at least 5, but I would say definitely no less than 5.
Okay. Awesome. Thank you.
You're welcome. And that's a general rule with my classes and my practice tests in general. Like I said, you're not gonna, unless you did like 20 iterations, you're not gonna get to see every problem. But the more you do take, the more chances you have of seeing every problem that will be on the test. Even though I reserve the right to change up to 20% of the points with questions that you didn't have access to. I just haven't done that in years, so you might as well just do the practice tests as much as you can. Anything else, anyone? All right. Well, it doesn't look like you guys have a lot of review type questions to go on. So let me, I think I'm going to go ahead and solve some physics problems for you guys from chapter 10. So what I'm going to do is ultimately going to share my screen. Let's see if I can do that and just make sure my iPad's on. That's helpful. Yep, my iPad's finally on. Now I got to go back here and choose a different one. Uh, so hold on a second. I'm just adjusting the name of my file so I can put it up. This is still time for you to ask questions if you have any. And the day is April Fools. My Tar Heels lost. Did you guys see that? But Duke managed to stay in it, and NC State managed to stay in it. So that's kind of cool. I don't usually pull for Duke and NC State, but once Carolina and East Carolina are out of it, then I definitely pull for an ACC team. All right, so I've got the app working on my iPad, so I should be able to share it now. It should come up any second now. So this is what we're covering in chapter 10, rotational motion. I'm going to say, let's go to example 1. And what I'd like to do is a car tire rotates through 7.7 revolutions. How many degrees is that? And part B, I'm going to call that A, so I'll just put that there and put a decimal, excuse me, a decimal. B, how many radians? Okay, so the solution here is pretty straightforward. Probably you've already figured out how to solve this. I hope so. It should be that straightforward. But what we have is basically theta. That's the variable that represents the displacement, which we call the angular displacement in this case. So this is just like the x before, and this theta is 7.7 revolutions, which you could also call 7.7 rotations, are 7.7 cycles. All those are sort of synonymous phrases. So if I want to take part A, what I can do is I can say 7.7 revolutions. Oops, almost wrote a rad there. 7.7 revolutions. I'll put that over 1 just for unit conversion purposes. It makes it easier to remember that that's a fraction and that's the numerator of it. What we know is 1 revolution is equal to 360 degrees. That's also true for 1 rotation. That's also true for 1 cycle. So with that, this tells us all we have to do is take 7.7 and multiply it by 360. And that gives me 2,772 degrees. Okay, so that's one answer. Now the other answer, we're asking for basically how many radians is that? So 7.7 revolutions. There I go again, right? These reminders are not helping me. 7.7 revolutions over 1. What we know is 1 revolution is equal to 2 pi radians. And remember, radians is actually formed from the equation. Let's write it over here. S is equal to R times theta. And it is the definition of radians. In fact, you can see that this implies theta is equal to S over R. So if you measured S in meters, you'd have to measure R in meters, and you'd see that the meters would cancel out. And that shows you, in fact, that radians are actually a pure number. So it's convenient to drop them at any time you wish, and it's also convenient to add them anytime you wish. Within reason, of course. I mean, there's no reason to introduce rotational motion when nothing's rotating, for instance. But with that in mind, we can now do it, and we're basically going to take 7.7 and multiply it by 2, which gives me 15.4. So a lot of times people would prefer radians in multiples of pi, in which case you'd say 15.4 pi radians. Or you could say times 3.14159, that's 48.38 radians. Okay, again, we're only using 2 sig figs, so all these extra digits, the 7 and the 2 there, the 4 there, the 3 and the 8 here, they're all literally not significant. They're just extra digits. Any questions on that one? So what you need to know is basically there's a measurement system, which hopefully you already know because you had trig, and in there you use radians, but it's a whole different measuring system. And in fact, you can talk about not only radians, where 2 pi radians is equal to 360 degrees. So that means you have a conversion factor of 2 pi radians per 360 degrees, or you can have 360 degrees over 2 pi radians. And of course, you use the one that you need, depending on where the unit that you're trying to cancel out is. So for instance, if the unit you're trying to cancel out is degrees and the degrees in the numerator, then you'd want to use the first version, which has a degree in the denominator. But that is not necessarily the most convenient. You can also see that another conversion would be pi radians over 180 degrees, which is also 180 degrees with pi radians. So that's another one as well. And just for the heck of it, if you actually want to figure out how many degrees is 1 radian, you can just take 180 and divide it by pi, and that gives you 57.29 essentially. So that's 57 point, actually let's call it 57.30. So 57.30 degrees equals 1 radian. Okay, so those are all different conversions. I will tell you that we have degrees, so that there are 360 degrees in a circle. In other words, if you make a complete rotation, that's a 360 degree rotation. But then there's also 1 arc minute, and 1 arc minute is 1/60th of a degree. And then there's 1 arc second, and what that is essentially 1/3600th of a degree. But you could also write it as 1 arc second is also 60 arc minutes. So that could help you as well. All right. So those are some further things to narrow down in terms of terminology that you might run into. I think I saw a couple problems within chapter 10 where they actually used arc minutes and arc seconds. For instance, if you've ever heard of the term parsec, okay, and hopefully you didn't learn about it from Star Wars, because if you did, you got a false a false definition. A parsec has something that looks literally like a second in it. It's a parallax second, but what they mean is a arc second. And what is done to bring that about is this. If you imagine this is the Earth, and we're actually in rotation, say from here to here around the sun, obviously not to scale. If we see a distant star out here, then what we see from this angle is it's over there. But when we're over here, 6 months later, we see it as this angle. But in fact, this angle right here is twice the parallax angle. So this angle equals 2 times theta parallax. So if you actually measure that angle in arc seconds, then you get this nice little formula that says the distance traveled, or the distance away that a star is 1 over the parallax angle in seconds. Okay, so that's where the parsec came from. Basically, they found out that once you do the trigonometry that's necessary, or the geometry that's necessary, if you find a specific star or planet that has a parallax angle of 1 arc second, then its distance is called a parsec, which is about 3.26 light years. So 1 parsec is equal to 1 PC, and that's about 3.26 light years. So that's most of the extraneous stuff, if you will, that we would cover in this chapter, in addition to what we already know about degrees and radians and all that good stuff. So hopefully you already knew about arc minutes and arc seconds. And hopefully that also reminds you that the degree is an arbitrary number. And that's why it's perfectly reasonable to have a degree Celsius, a degree Fahrenheit, a degree in geometry, a second as a unit of time, an arc second as a unit of angle, arc minute as a unit of angle as well, and a minute as a unit of time. Okay. Other than that stuff, we also have, like I said, S is equal to R times theta, which you can take the derivative of and get V tangential is equal to R times omega. And you can also take that and get A tangential is equal to R times alpha. And then there happens to be yet another acceleration, A centripetal, and that's the V squared over R that we did in, I think, chapter 6-ish, maybe 5, 6, something like that. Any questions on that?
I have a kind of conceptual question.
Yes. Go for it.
So the formula for centripetal acceleration is it uses in its derivation like the angular like qualities of a circle rotating with like
Right.
omega and everything and substitutions. So how's kind of like the relation between that and like these quantities, just like roughly?
Right. Okay. So in actuality, it is actually a very profound thing. For instance, if you imagine something traveling in an arc, which I'll draw right here in purple. So that's an arc of a very specific radius, right? If you're right here and you hit the accelerator, then that's going to cause an acceleration this way, and that is a tan. That's your tangential acceleration. But in order to maintain a circular path, you also need, perpendicular to that, a centripetal acceleration, a sub c, so that what you get is in fact the total acceleration of the object would be this vector. So it's two that shouldn't really mingle. So B tangent, the V equals R times omega, that is the angle, or excuse me, that's the angular velocity along the arc length. So that one actually shouldn't have much to do with a centripetal, except for the fact that it uses basically that velocity in the numerator squared divided by R. Does that make sense?
Yeah, I'm liking that.
Okay. So yeah, that's the big deal, and occasionally they'll throw in a question like that where they want you to know answer the entire acceleration. So what's the total acceleration? That's what they're trying to get out of you at that point. They're wanting you to show them or show me, since I'm the instructor, that there's an acceleration that's tangential to the path, and then if it's actually going in a circle of arc or any non-straight line, there must be some kind of acceleration causing it to deviate from that straight line. If that happens to be a circle, then it's a centripetal equals v squared over r. Okay. And these equations, let me go ahead and circle them. These equations you use over and over again, and they're only valid with radians, radians per second, per second, those three. This one, of course, you've already grown familiar with, and that has nothing to do with it. And these constants, of course, are important. Relating, for instance, radians to degrees and all that good stuff. These guys are important as well. So that's sort of all the stuff, if you will. And then the problems are just pretty straightforward. So let's say, here's another example. A merry-go-round. Oh no, I hate when this erases. A merry-go-round is initially at rest. I'll say at t equals 0. And it is pushed so that it experiences an angular acceleration of alpha. Notice I went ahead and gave it the symbol. That's sort of the part of the learning in this chapter where you got to figure out what symbols to give it to you, but I'm doing it now to help you familiarize yourself with it. Let's say at 0.080 radians per second every second. Again, you can write this as radians per second squared, but just like I told you before, to understand physically what acceleration is, it probably helps to write it as and read it as radians per second every second. So what we're saying when we say an object has an angular acceleration of 0.080 radians per second, that means if you start from rest, it'll go from 0 to 0.08 radians per second after 1 second, and then 0.16 after 2 seconds, and then 0.24 after 3 seconds, so on and so forth. Now that I've covered all that, I'm actually going to ask the question. So if we do that, what's actually going to happen? It's going to increase the angular velocity. So experience acceleration of this. And if this acceleration, actually, I'm going to abbreviate that. Actually, I'll just erase that and start on the next line. If this acceleration, darn it. Continues for, let's say, 10.0 seconds, what, and that should have been lowercase, what will be its final angular speed? So that's part A. Part B, through what angle will it have rotated? And let's see. C, what is the tangential acceleration for a child 1.00 meters from the center and or a dog at 2.00 meters from the center. Okay, so that's a pretty straightforward, typical kinematic type problem. Anybody have any questions about what I'm saying here? Anybody don't understand necessarily anything that's going on? Have any questions? All right. So what we're going to do is part A. They want to know what will be its final angular speed. Well, there's a bunch of ways we could do it. For instance, we know we used to have V is equal to V0 plus AT. So that certainly works. In this realm, it would be omega is equal to omega 0 plus alpha t. So in this case, I'm going to say omega is equal to 0 radians per second because it's starting at rest, okay? And plus alpha is 0.080 radians per second times 10.0 seconds. So you can see that omega is going to be 0.80 radians per second. That's the final velocity after that 10-second interval. Does that make sense to everyone? Okay. B, through what angle will it have rotated? So let's attack that now. We know, for instance, that well, there's a couple of different ways we could say, well, actually, I'm going to always tie it back to the linear motion. So we could say x is equal to 1/2 alpha at squared plus v0t plus x0. That gives us theta is equal to 1/2 alpha t squared plus omega 0t plus, oops, almost right, x0 plus theta 0. You always can assume the x0 or theta 0 is 0, and that's what we're doing here. In this case, the initial speed was 0, so we can actually use this equation and say theta, oops, wrong color, and say theta is equal to 1/2 0.080 radians per second times 10.0 seconds squared. And in this case, you see it's going to be 100. 10 squared is 100. So if I multiply 100 times 0.08, I get 8.0, and then times 1/2, I get 4.0. So 4.0 radians is the distance traveled. Notice that's the only unit that actually works. And of course, I could say that is a certain number of revolutions by dividing it by 2 pi. So 4 divided by 2 times 3.14159. That gives me 0.637 revolutions. Okay. In other words, 4 radians. We already found out that a radian is about what, 56.30 degrees, as I wrote here. So these quantities are all helpful. 57.30. So obviously 4 radians would be 4 times 50, that's 200. 4 times 7, that's 28, that's 228, and then 229.2. So 229.2 degrees. That should be divided by 360, should be about 0.646 which is exactly the same number of revolutions. That makes sense to everyone? So those are some answers we could do. And I just worked out that it indeed does work out to be about 0.637. Now for part C, they want to know what is a tan. In other words, the tangential acceleration for a child 1 meter from it. And from that, we know not an equation that has a parallel in linear motion, but specifically what we know is V is equal to R times omega. So in this case, we're going to say the distance from the center of rotation is 1.00 meters for the child, and then the omega is 4.0 radians. Actually, no, I copied the wrong figure. Let's fix that. The the final speed at that point is 0.080, or excuse me, 0.80 radians per second. So if I multiply that by 1, I see that I get 0.80 meters per second is the speed. Notice how I just threw away that radians. That's why I took the time to tell you guys that a radian's not technically a unit at all. It's a meter divided by a meter, or a centimeter divided by a centimeter. So it's really just pure number. But that's what it is. 0.80 meters per second is the tangential speed at 1 meter from the center. And the more important thing that I'm trying to show you with this problem is that basically that velocity, that tangential speed, does actually change at different locations on the merry-go-round. However, the angular speed is always the same, 0.80 radians per second. So in this case, we're asked for the center for a dog sitting at 2 meters from the center. I said the center. And I said from the center twice because I just wanted to make sure I used really bad grammar. So we're going to go with that. So now we're going to do for 2 meters, and I'll say velocity 2.00 is equal to 2.00 meters times 0.80 radians per second. So this time we get 1.60 meters per second is the angular speed. And that's one extra sig fig there. But you can see clearly the dog, being 2 meters away from the center, is experiencing a higher tangential speed than the kid is when he was 1 meter away. But the nature of what we call rigid bodies is that the angular speed, which is given by either omega or revolutions per minute or radians per second, that's going to be the same for the entire disk. Okay, so you got to keep that in mind. Anybody have any questions on that? Now we did use theta equals 1/2 a t squared plus v0 t. For the record, we could have also used v squared is equal to v0 squared plus 2a x minus x0. Its rotational analog was omega squared is equal to omega 0 squared plus 2a theta minus theta 0, which again, I'd call that theta 0, 0, and I'd call this omega 0, 0. So we can see in this case, if we wanted to know the actual theta, we could say theta is going to be equal to omega squared over 2 times alpha. Well, the omega was the final, so that's 0.80 radians per second squared divided by 2 times 0.080 radians per second. So if I do that, I get 0.8 divided by parentheses 2 times 0.080. Oops, I forgot to square my 0.8. Let's go back and fix that. So 0.8 squared divided by parentheses 2 times 0.08 close parentheses, and that gives me 4.00 radians, which is exactly the answer we got before. Okay, so that's a check And like I said, that's just another thing you can do to double check your work is obviously try to solve it from a different standpoint or from a different equation. And if you have multiple ways of calculating and all point to the same answer, then you're a lot more confident in your answer. Any questions on that? All right. Here's a question which is not unlike questions that you possibly should be ready for on the face-to-face exam. So let's look at this example. Oh, there it is. Let's say, whoa, Nelly. All right, baby, drive carefully. I love you. Hold on a second. My daughter's leaving to go back to school. That's good. Love you. Have a good one. Nice seeing you, Benny. You're welcome. Sorry, everybody, I'm back now. So example 3, I'm going to say, dang it, I'm going to say erase a bunch of stuff. If anybody knows how to get this good notes to stop going to erase every time I stop writing, I would really appreciate that help. So let's say, consider a disk rotating at omega equals, let's say 2.4 plus 1.2 t radians per second as the unit. So that's the angular speed. Consider a disk rotating at that angular speed with a radius of, let's say, 4.00 meters. Determine oops, that went really badly. And when I want to change it to erase, it hardly ever works. Determine the angular acceleration now that's the angular acceleration, so you probably know what we're talking about here, but just in case, I'm getting ready to say it, so I want you to think what symbol I'm getting ready to say. Angular acceleration, that one, alpha. Okay. At t equals 2.00 seconds. And actually, that's not a question, so I'll just put that. B, what I'd want to do is, that's the angular acceleration. Let's see. I want to do B, what is the A total? Okay, so that's what we're going to try to do here. So what we're using is a very specific set of equations. For instance, we know that alpha is equal to d omega over dt. So we can use that. We also know that V is equal to R times omega, and we also know that A is equal to R times alpha. And finally, we know that centripetal acceleration is equal to V squared over R, and that this specific velocity is V tan. All right, so let's go with this. For part A, what we want to know is determine the angular acceleration alpha at t equals 2 seconds. So alpha is equal to d omega over dt. If I take that derivative, the derivative of 2.4 with no t is just 0, but the derivative of 1.2 t is 1.2 radians per second. So not only is that the acceleration at t equals 2.00 seconds, that's always the acceleration basically. In other words, it's a constant. So in this case, we have alpha is equal to 1.2 radians per second at t equals 0 and at t equal 2.00 seconds. Does that make sense to everyone? Now for part B, you want to find the find the speed V. Actually, well, we're going to find it because we need to find A total. What we know is, A total is equal to A tangential plus AC, which is center seeking. So A tangential is equal to R times omega. And what we want to do again is at 2.0 seconds. So I'm going to say at t equal 2.00 seconds, we have A tan is equal to 4.00. Now, since I've chosen that the thing has a radius of 4 meters, we're actually calculating the acceleration of the outer edge. I just want to clarify that. So it's 4.00 meters, which is why I use that, times the angular acceleration, which is 1.2 radians per second. And actually, that was supposed to be radians per second because I divided it by t. So I'll put per second like that. So now what we're going to get is 1.2 times 4. That would be 4.8. 0 extra significant figure meters per second every second. That's the tangential acceleration. And then AC would be V squared over R. Well, V is equal to R omega. So that's 4.00 meters times omega. In this case, omega is 2.4 plus 1.2, where that time right there is 2.00 seconds. So basically I ran out of room and I had to write it like that. So when I multiply 4.0 meters times 2.4 plus 1.2 times 2, the 1.2 times 2 becomes 2.4. That added to 2.4 becomes 4.8. And then 4 times 4.8 is 16. And then 4 times 0.8 would be 3.6. So this should be 19.6 meters per second. Double check that. So that's 1.2 times 2 is 2.4. 2.4 plus 2.4 is 4.8. 4 times 4 is, of course, 16. And then 4 times 0.8 would be 3.2. Oh, 3.2, not 3.6. So 3.2 plus 16 should be 19.2. Sorry, I wrote that it was 19.6, but that should be helpful. Now I can take that 19.2 and plug it into V squared over R, again, talking about the edge. So this would be 19.2 meters per second squared divided by 4.00 meters. That's 92.16. Meters per second. So in fact, you could make, it's actually called a Fermat frame. So you can always make a coordinate system where no matter where you are, and you can use your trajectory, you can use the path along which you're riding as one of the coordinate directions. That's part of the Fermat frame. Then you use something called the Graham-Schmidt process that would actually allow you to generate the other unit vectors. And by doing so, you'd have a three-dimensional Fermat frame that rides along with your spaceship or whatever you're riding. In this case, what we're going to say is we're going to say the tangential direction is in the x direction, and we're going to say the centripetal acceleration points in the negative y direction, because it's got to be perpendicular to x. And if I see x is going this way, then clearly y going down would be pointing to the inside of the circle. So that's a scenario. So what I can say is a total is going to equal 4.80 meters per second in the I hat direction. And then I'm going to say, because I chose it to be in the negative y, would be the negative centripetal direction. That's going to be 92.16 meters per second in the j hat direction. Again, the negative indicating that it points downward. So if we look like this and this, that would be our x direction, that would be our y direction. And what we're imagining is an arc like that, and just at this particular second we have an acceleration a total that way, which actually is not really that well drawn to scale, but you see basically what we're talking about. Anybody have any questions on that one? So the radial part, of course, is, like I said, 92.16. So that'd actually be a lot bigger than the tangential part, which was only 19.2. So it's, about 4 times bigger downward than it is rightward. That's why I said it's not to scale. No questions? All right. Well, I've gone long enough, I think. This is just through section actually 10.1 still. There's a lot more stuff to cover. I don't want to, overburden you the day before an exam or anything. So those of you who have my exam tomorrow or Thursday, I definitely want you to just go off and do that. The rest of you guys that are in my 241 day class, your exam's not till Monday. So get working on that and try to keep up with your homework. And Wednesday we'll do some more problems, and I'll finish up chapter 10 and jump into 11. You guys are free to go. I'm having another one at 3 you're welcome to come to, but until then, or excuse me, at 2 that you're welcome to come to, but until then, I'll see you.
Just to clarify, it's chapter 10 this week for homework, and that's like it.
There might have been, I might have moved it such that chapter 9 is still available, but other than that,
Yeah.
yes.
Awesome.
I'll double check the date real quick. I'm pulling it up right now, as you said. Even if I finish 10 on Wednesday, I'm not sure I'm going to keep it due on that day. Yeah, so 9 was due last time. I'm going to move chapter 10 to Sunday. So I'm going to basically move that back right now.
Okay. Have a good one. Thank you.
You too. Thank you.
I have a question about the problems you given.
Yes.
So why the A total, the Y component of the A total is negative again?
Oh, okay, that's just the direction I chose it to be. It didn't have to be negative, but because I chose it to point in the negative y direction, that made it come out to be that.
Oh, okay, got it. So it depends on what position we are taking on, right?
Yeah, or what coordinate system you chose at a particular position. So I was trying to pretend that's like the top of an arc and that the object was actually moving to the right. But it's also moving in a circle whose center's down below. So in order for it to accelerate towards the center, it must accelerate downward. That's why that gave us the negative.
Okay, thank you. Got
You're
it.
welcome. Kayla, Tommy. I know Tommy. All right. I'm not sure anybody's left here. Tommy, you still here, bud? Oh, he's gone. And we'll end.